Good morning. Are virtual threads going to make reactive programming irrelevant? Who could think about a better Beatty title to lure people in a room and talk about that? So in case you feel kind of cheated by this title, the answer is yes. So if you want to go and have a coffee, you can do that. And if you want to understand why, well, this is what I'm trying to explain you over the next 50 minutes. So my name is José. I work at the Java Platform Group at Oracle as a Java developer advocate or something. And I decided that I was done doing slides with links, so I just put a QR code, and if you're interested in the links, you can just follow it, which is nice because even if you follow it next year, I will update the GitHub page that you will be taken to, so it will be updated automatically, which is actually a good thing. We develop a website at the Java Platform Group called the dev.java website, which is this one. You can connect there if you have many elements of documentations on many aspects of the Java platform. There's a lot going on currently on the Java platform outside of the Loom project, which we are going to talk about now, that you can discover if you want to visit that. This is the written content we produce, but we also produce video content. We have a YouTube channel that is pretty active, where you can have lots of different formats of videos. Maybe some of you already know that. My friend Nikolai is doing the Inside Java newscast, which is about every 2 weeks. I'm doing the Jeb Cafe, and not enough. I would like to spend more time on it, but yeah, don't have. There are only 24 hours in a day, so you know. And I'm also doing shorts. My friend Billy is also doing the SIP of Java. And we're also doing a podcast called the Inside Java Podcast, if you're not in video. And if you don't like written content, if you don't like videos, and if you don't like audios, well, I think we are out of content for you, unfortunately. And probably out of ideas also. Right. Everything I'm going to talk to you about is actually taken from the OpenJDK website, which should be also your one-stop website when you want to have really on-the-edge news of everything related to the Java platform. The OpenJDK is actually an association of people working on the specification of Java. So you cannot download the OpenJDK. It would be like, I don't know, downloading the City Hall of Stockholm. Doesn't really make sense because it's a group of people. But you can definitely go there and check all the distribution there are. Distribution that you can find on the jdkjava.net page. And you can see that you already have early access version of the JDK 24, which is to be released in a few weeks, and also of the JDK 25, which is to be released since September. Maybe some of you are still on this old JDK 23 release? Yeah? Oh, nobody. Okay, so you're already on 24. That's great. And we're going to talk about the Loom project, which is the project that works on virtual thread, that delivered virtual thread a while ago. The first preview version delivered was in the JDK 19. That was already 3 years ago. Well, 3 years in May, so not exactly 3 years, but almost. That was a huge engineering effort. As you can see, that's the pull request, all right, for the Loom project, the first pull request on the main JDK branch. There's something like 100,000 lines changed, many files. Everybody knows about code reviews? Yeah? So there was a code review on this pull request. It took several days, as you can imagine. It was integrated as a final feature in the JDK 21. That was not 2 years ago, but well, I'd say 18 months ago. And so virtual thread are now a final feature of the JDK, which is great. By the way, this is the JEP 444. JEPs are documents that are meant to be read by normal humans. That is, they are not the aliens. Oh, the aliens are not there anymore. Not by people who have to implement the feature. These are not specification documents. They are really educational documents. They explain you the why, the how, they give you patterns of code, etc. So if you have never read any JEPs, you can definitely connect to the OpenJDK on the JEP page, where you have all the JEPs since the beginning. By the way, the first JEP was JEP 1, and the second JEP was JEP 0. probably because we were frustrated because there was no JEP0. Okay, so now you have this virtual thread, you can definitely read it. There are other parts of the Loom project. The other main part that you probably heard about is the structured concurrency part, which is still a work in progress. It will still be a preview feature in the JDK 24. There is an early access version of the Loom branch that you can download from the JDK Java.net website. And in it, there is the new version of structured concurrency, which differs from the one you will have as a preview feature of the JDK 24. Right? Doesn't differ by much, but it's still different, meaning that in 25, structured concurrency will still probably, it's not done yet, but still probably a preview feature. And the same goes for scope values. Scope values are meant to be a replacement of thread local variables. And it's still a preview feature in 24, and will probably be still a preview feature in 25. Everything you need to know is explained on this link, jdkjava.net/loom. This is where you want to go if you want to get the mailing list, the documentation, the early access versions, and if you have feedback on everything that is being developed currently in the Loom project. As for the adoption, because preview virtual threads are a thing now, well, every major framework around has something related to virtual threads. Whether it's new patterns, whether it's a new framework, whether it's new anything, annotation stuff, literally all the major framework around are doing something with virtual threads. So what I would like to show you is how virtual threads are going to change the way you write your reactive code, you write your reactive programming applications. This is what I would like to show you. What does it mean to be irrelevant? Because this is the word I use. I didn't use the word useless, because it's not the same meaning, actually. Irrelevant means that you can still use reactive programming, of course, if you want, but you don't have to. And if you decide to embrace virtual threads, you will be able to do the same thing in a simpler way and with different things that are going to be in it for you. And this is what I would like to show you. Virtual threads and reactive programming are about to solve the same problem. Okay? They solve the same problem. Is there a tool better than the other? This will be to you to decide. Do you want to embrace virtual threads or stay with reactive programming? This is your decision. I'm not in your shoes, and I don't know your application, so it's really a decision you need to make. But you need to make an informed decision, and this is what I would like to give you today. Reactive programming has been there for more than 10 years now, 10 plus years. You know exactly how it's working. You know exactly how people are working with it, how you can debug it, how hard it could be to write reactive code or to maintain reactive code. You already know that, so that's great. Virtual thread and structured concurrency, on the other hand, is not exactly there yet. We have virtual thread, but we don't have structured concurrency yet. So we are on the edge of having it. We've never been so close, of course, but we are not there yet. Okay, so we are mostly relying on promises. Concurrency is hard. It's supposed to help you get the best performance out of the multi-core CPU you have. We are not going to talk about every aspect of concurrency. We're going to talk about one aspect of concurrency, which is achieving the best throughput for your application. So we are not going to talk about in-memory computations like virtual threads or this kind of, like parallel streams or this kind of thing. We're going to talk about really about throughput. And as of now, the paradigm we use in programming to achieve the best throughput possible is to use this callback-based reactive programming approach. It comes with its drawback, but as I just said, we know exactly how it works, which is probably for the best. And we could ask, the first question we could ask ourselves is, why do we need that? Why do we need reactive programming? Why did people came with this solution? Why did they build that, and why were using it? If it was not a good solution, nobody would be using it. And many people are using it, if not everybody is using it. So there must be good ideas for that, behind that anyway. So the first thing I would like to come with is a very simple example where you are trying to build a page. And to build this page, you need images and links. It's funny because there's only one image and several links. Maybe it should be several images. Never mind. All right, so you are calling a service that is reading images from the internet and reading links from the internet, and you merge them together, and you bring a page. And you know that if you write this code like that, in that way, because in read image, read links, you have internet requests, it will take in the order of the tens, if not hundreds of milliseconds. So this code is going to take forever to be executed. So this is not the code you want to run on your application. Running this code 25 years ago, in the early 2000s, at the beginning of the internet, was okay. Why? Because the internet was so slow that waiting for 200 milliseconds was just the norm, right? And because you only had like 5 clients a day to deal with, there was no problem with that. But it's not the case anymore, so we need to be smart. So the first solution to that was in 2004, a little more than 20 years ago, when the executor service pattern was introduced. And we're saying, okay, we are going to run every request in its own thread. So at least these requests are going to be executed in parallel. Okay, so instead of waiting for 100 plus 100, we are going to wait for 100 and then merge the result because we'll have both results almost at the same time, right? Apart from the fact that I'm using the var keyword and the method reference that is lambda expressions, this is a 2004 pattern. The executor service pattern is Java util concurrent. That was 21 years ago. All right. The problem is that this code comes with bugs. And there are a number of bugs in this code. There are obvious bugs, and there are sneaky bugs. And I'd like to talk to all of them. First, you are blocking threads. And blocking threads is bad. Why is it bad? Because I heard so. Okay. Why is it bad? Maybe we'll talk a little more about that in a minute. Okay. So how many threads am I blocking here? Well, actually, I'm blocking 3 threads. If I have more than one thread in my executor service, because the first line is blocking a thread from the executor service, and the second line is also blocking a thread from the executor service. But the main thread that is actually calling this is also blocking because I'm calling get, and this get call is blocked by the previous thread. So I'm literally blocking 3 threads. So if it's bad to block a thread, it's probably even worse to block 3 threads, right? So I would say that that's the first bug. Blocking a platform thread is wrong because there's something that you can't do with platform threads. That is, once you've submitted a task to a platform thread, whether it is a runnable or a callable, there is no way you can detach this task from this platform thread. So if this task is just sitting there doing nothing, your platform thread is doing nothing until this task either produces a result or produces an exception. And you cannot stop a thread from the outside, and you cannot cancel a thread from the outside, even if you have the methods on the thread class. And if you don't know why, I invite you to read the Java doc. There is a very good explanation of that. Okay, so you cannot stop a thread from the outside, and if your task is not stopping it from the inside, well, nothing is stopping this thread. All right, so that's one of the reasons why it's bad to block a platform thread. The second bug is a little more sneaky, is that it can lead to lose thread. All right, because if you check carefully the first get that you're calling, and you suppose that this get crashes not because of timeout, but because of something else, then the second get is never called. So imagine a situation where read images throws an exception. This exception bubbles up to the thread and to the get method that you call on this future object. But then, because the same thread is executing the first get and the second get, this second thread is also going in the catch block. And so the second f2.get is never called. Now, if something is also going wrong in read links, like read links runs forever, never stops, then you end up in your executor service with a thread that is not doing anything, that is blocked forever, and you cannot use it for anything else. And this is really bad because you spend hours fine-tuning your executor service, and you know that the best number of threads is 12. 13 is too much, 11 is not enough, 12 is the perfect number. And after 3 days, you realize that actually your application is running only on 11 threads. There's one thread that is kind of lost, and you can't know what it's doing. You don't have any tools for that. And after 3 more days, you go from 11 to 10, and then to 10, from 10 to 9. And then what do? Well, you reboot your application, because that's the only thing you can do. All right? You boot your application, wait for another week, and then after a week, again, you have only 9 threads that are available to your application and your tasks. What's going on? How can you fix this problem? Well, apart from reading your code thoroughly and spending hours there, there's nothing much you can do. You're done. You have loose threads, and the bug is there. You're calling 2 gets in the same thread, and you shouldn't be doing that. That's annoying, and that needs to be fixed. And the third problem is that it's hard to debug. You know this problem you have in read images, this exception that is thrown sometimes, and that causes this problem? Well, if you examine the stack trace, and I'm going to show you these stack traces, if you examine the stack trace of this, it does not take you in your application where you would like to go. That is where the bug is actually happening. It takes you in a stack trace of this thread that is launched in this executor service, because this executor service is actually launched along with your application, when you start your application, it takes you in a process that is starting your application, not in the application where you actually submitted this read image lambda. Okay, so that doesn't help you. So that's 3 problems, and 3 problems that basically you need to fix. You want to fix these problems. All right, we've been living with this problem for years, like for 25 years, since Java was there, 30 years. But there is a time where you need to sit and say, okay, enough is enough. Now we need to fix that. So we have 3 problems to fix. Blocking a platform thread is bad. Excuse me. Having a non-relevant stack trace is bad, because it doesn't help you in debugging your application. And having loose threads is bad also, because it's a bug, and you want to get rid of this. So let us go back a little one step and ask ourselves, what is a platform thread? The thread class has been there since the beginning of Java, about 30 years ago. Okay, you have this Java long thread class, which is a wrapper on what is called a kernel thread or a platform thread, that's the same actually, that is given to you by your operating system. It's a operating system resource. Creating a platform thread takes about a millisecond and will allocate upfront in the order of the megabytes of memory. 2 megabytes is a good assumption, right? And if you know what context switching is in the order of 100 microseconds, so it's a lot. So these limitations, and especially the memory limitation, make it so that having more than several thousands of platform threads alive on your machine is actually a hard limit that is imposed on you by your operating system. You can certainly not have 100,000 platform threads on your machine. You can only have several thousands of them. And actually, if on Linux or on macOS, you just try to create new thread in loop, you will hit a limit very soon, before 5,000. Why is it wrong to block such a platform thread? We're going to talk about that also. The first paradigm 20 years ago, maybe there are still some J2EE architects in the room. Yeah, good. I can see some how to tell your age without telling your age. So back in the days, in these days, the paradigm was one thread should take care of one client on a web server, and everything was executed in the same thread. One network request, one thread. But if you live with this model, it means that you can only manage 4,000 concurrent requests on your machine, which was not a limitation 25 years ago, but which is a limitation, and a very strong limitation today. But on the other hand, you could say, all right, managing a network request, you see, creating the request, decoding the response and marshalling the JSON I get and everything, this takes in the order of the microsecond of CPU time. So if I just take a look at the CPU and not at the thread I can have, my CPU should be able, each core, of my CPU, should be able to handle on an average of 1 million requests per second. So on the one hand, I have a thread model that limits to 1,000 requests, and on the other hand, I have a CPU that can manage 1 million requests. So I have a factor 1,000 between both. All right? And 1,000 is a lot. That's a lot. Okay? So whatever you do, you need to gain this factor 1,000 on the way your threads are managing your request to hit the CPU limit. You cannot go past this CPU limit because, well, you can't. So it means that the model 1 request per thread, sorry for you guys, it does not work anymore, okay, due to this capacity CPUs now have. So here you have two solutions to gain this 1,000 factor, 1,000x performance gain. The first solution is the reactive programming solution. And basically what you're doing is that you have one platform thread that is actually handling many requests. You divide your requests in small atomic operations. You wire them using your reactive framework. You encode them in lambda expressions or function calls, which is basically the same. You send everything to the reactive framework, and it takes care of the rest. And it works well, and it has been working for more than 10 years. And you can achieve amazing performance with that. If you take a look at the patterns of code you have, you go from this pattern, which is not great, which doesn't work, it has bugs, we saw them, but which is simple to understand, simple to write, and simple to maintain, to this pattern of code, which is the completable future way of writing it. So you may be using other reactive framework, but basically this is kind of the same, right? So you create, as I said, you just divide all your processes small lambdas. Each of these lambdas should not be blocking, and we're going to see why. All right, and you wire them together with a programming model which has nothing to do with the classical programming model you know. No for loops, no while loops, no try-catch, no nothing of the, you cannot use any of the language constructs that you have and that you know how to use, okay? How is your platform thread being used when you're using such a code? Well, this is a platform thread, nice green arrow. You didn't know it was actually, it's that simple. No, I'm kidding. It's much more complex than that. But never mind. All right. So you send your first lambda to it, and this lambda will execute in a matter of microseconds. Then this lambda is doing a network request, and what you're saying is that once this request is done, I'm done executing this lambda, and you should call the next lambda in the chain when the data is there. How does your reactive framework know that? Well, it registers a handler on an operating system signal that will tell the framework, hey, the data is there, so now you can call the next lambda in the chain. All right? And this will be done probably in a matter of milliseconds after that. Okay, so between these two little boxes, you have about 1 millisecond, during which your thread is doing nothing, but it's not blocked executing a lambda. It's doing nothing, but it's available to do something else. So that's the biggest difference with the previous pattern with the executor service. Well, this thread was actually blocked by a task that was not responding. Okay? And maybe the second lambda is doing another request on the database of some sort or whatnot. It will then stop its execution, and the framework will know that after a while the data is there, and it can call the next lambda on the chain. All right? But in the meantime, this thread is available to execute another lambda that will do the same. Send a request, wait for the response, and when the response is there, then the framework will call the next lambda with the data it needs to do its processing. And again. Okay? So in the end, if you do that the third time, and then a fourth time, and then a fifth time, and then a sixth time, you can see that actually you end up with a platform thread that is used all the time, thanks to this nifty framework that is actually doing the job in the background for you. So you pay the price of writing a code that is complicated, that is complex, more complex than a simple imperative code. But the gain you have is that you have a platform thread that is used 100% of the time, and that is actually doing things. There is one thing that you should absolutely avoid, and I'm sure that you already know that, by the way, is that if one of these lambda expressions is actually blocking because the code you wrote in it is faulty, then it actually blocks all your process and has an impact. It has actually an impact on all your application. And this is bad. If you have such a lambda as your application, you need to track it, and you need to fix that bug, because it's a bug. It's on your shoulders as a developer to write lambdas that are not blocking. And if you do that, it will have an impact not only on the process you're in, but on all the application, because all your application is actually sharing a very small amount of threads that are doing the job. So that's an important point. Now, suppose that something wrong happens in read image. You remember this read image? There is a sneaky bug in it. I didn't show you the code because the code actually doesn't exist. It just throw new illegal state exception, and that's it. Well, if you are in the executor service pattern, if you're in a main thread and you get the stack trace, well, you have my app, line 27, that is calling read image, and in some service on line 12, you have the faulty stuff. So if you want to put a breakpoint somewhere, because you want to debug in a step-by-step approach, or if you want to check the code, you know that this is happening on line 12 of your some Java source code, which is great. You know exactly where you would need to look at your code to get the information you need. Right? Your stack trace takes you where the bug is actually. What is happening when you're in this executor service pattern? Same pattern, but in the executor service one. Well, this is the stack trace you get. You get a first stack trace telling you that, yes, my app actually failed on the get call that you have on line 32, because the bug is happening within the thread, and it bubbles up through the future API in the thread that actually is calling the get stuff. All right? And if you take a look at the caused exception, then you have a second stack trace that takes you to some service on line 12, which is nice. This second stack trace, you see that it takes you in thread.run, all right, because this is the executor service thread. So basically it takes you where this thread was created, and it was created when your application was created, which is not very useful to know because you already know that. But still it takes you to the line 12 of some service. So you know where this bug was happening. What stack trace will you have if you have a completable future, a pattern? Well, here you're in trouble because read image is executed on the second line of this code, but the exception is actually called by the framework and sent to another Lambda expression, which is passed to the when complete method. So it's not happening in the same context. You're not even sure that it's actually called in the same thread. The Lambda from the when complete passed to the when complete method may be executed in a different thread than the read images one. So the stack trace is this one. And you can see that it doesn't take you anywhere you would like to go, all right? You're in your completable future API. Everything is being executed in a common fork join pool. So you're in this thread. You can think about this thread as some kind of executor service, launch when you launch your application, but it doesn't take you anywhere you want, even in this code, by the way. You don't know where you are. And if you check, so that's the first stack trace you get. And if you check the stack trace of the cause of it, it also takes you to some service on line 12, so at least you know where it is. But where was it called from? If you want to have the context, well, you don't know, because the context is completely lost. This Lambda was passed as a parameter. It was wired by your completable future framework, and the context from where it was in your code is lost. You don't know where you are. So it means that if you put a breakpoint there, basically you don't know what code actually called you. And that's a problem when you're trying to debug that in a real application, knowing that actually this process was called this Lambda, then this Lambda, then this Lambda. Following a single process is actually very hard because everything is happening in different threads. So on the overall, excuse me, Asynchronous programming is efficient. There's no doubt about that. You can really literally achieve amazing throughput. And the throughput you can achieve is actually optimal CPU-wise, because your CPU is really used 100% of the time. But the programming model is hard to read, hard to write, hard to test, hard to maintain. We all know that. The problem is that it's impossible to debug. Because the stack traces are not meaningful, it's also impossible to profile. Actually, when you profile such an application, what you're really profiling is your framework and not your application. And don't writing blocking lambdas is actually on you. If you write a blocking lambda, that's a sneaky bug, and you need to fix it. So it comes with some drawbacks. So what was the effort of building virtual thread? The goal of building virtual thread is to fix all this. Not only performance, but actually all the rest also. And loose threads also. We didn't talk about that. We are there. The first solution that was taken is say, okay, we are going to split our business process into small lambdas and throw them all over the place, because we have a modular thread that is too heavy and we can't have more than 1,000 of them or several thousand of them. But you could also take another approach and say, what about building a modular thread that is actually lighter than platform thread? And how much time lighter? Well, it has to be 1,000 times lighter. On a machine where you can have 1,000 platform threads, you need to have 1,000,000 threads, virtual threads. You could be thinking, oh, this is marketing bullshit, this million thread. No, it's not marketing bullshit. It's actually a constraint. Because if you can only have 5,000 of them, then you will still need to rely on a reactive programming style where you split your business process in small lambdas to achieve 100% CPU usage, right? So this factor 1,000, this million thread is actually a constraint. It's the minimum you need to do. If you do less than that, it's not good. But it's not all about that. It needs to be as efficient, same throughput. Can it have a better throughput? Well, no, because you're already using your threads and your CPU cores 100% of the time. So you cannot achieve better throughput. If you can, it means that your reactive framework is actually not optimal. And you can think that, yes, it is. Second, to provide a simple programming model, making debugging possible and making profiling possible, and getting rid of loose threads. All right? And this is what has been done. I'm going to go a little faster above it because you probably already know that. A virtual thread is actually a wrapper. It's a regular Java object. Creating a virtual thread is as expensive as creating a string of characters. It's a regular Java object. It's a wrapper on a task, and this wrapper on a task can be moved from a platform thread that is executing it to the heap memory when it's blocked. Okay? And when the virtual thread scheduler knows that the data is there because it blocked on some internet request, knows that the data is there. How does it know it? Well, it registered on the same signal as your reactive framework did, right? Then it can take this virtual thread stack and bring it back on a platform thread. And because all this is happening on a four-join pool, well, if this worker is actually busy currently, it will be put in a wait list. There is this work stealing stuff that is being implemented, and it will be able to move on another worker. Okay, this is how virtual threads are working. And this is all built on continuations and stuff, but these are technical details. All right. The main thing that you need to take away from this is that blocking a virtual thread does not block the underlying platform thread. So writing a blocking code in a task that is submitted to a virtual thread is actually what you should do. If you don't write blocking code, don't use virtual threads. The threads of the garbage collector are not virtual threads. The thread of the JIT compiler are not virtual threads. Okay? Don't do that. If you are running parallel streams, don't use virtual thread. You will not get any better performance. Actually, you will decrease your performance because you will have the overhead of creating the virtual thread. Even if it's not big, it's still there, and you can measure it. How is your platform thread being used? Same question as reactive programming. Well, you have a virtual thread that is executing a code with a network request in it, And at some point, this network request will block waiting for the data. The virtual thread scheduler will take this virtual thread out in a heap, free the platform thread, and when the data is there, it will mount it back to carry on with its execution, right? And then another request will come, the platform thread will be unmounted, sorry, the virtual thread will be unmounted for the platform thread, and then brought back when the data is there, all right? And it will happen once more. Another virtual thread will be executed by the same platform thread from the fork join pool. It's not the common fork join pool, by the way, it's another fork join pool, but never mind. And then later it will come back with the data, carry on with the processing, be unmounted, and then be brought back to the platform thread. And again, and again, and again, and again. All right? So what is the difference between the reactive model and the virtual thread model performance-wise? Well, if you see any difference, it comes from the copy-paste that is not working in PowerPoint, because that's really a copy-paste. There's no difference. So if you think you're going to get better performance with your by mounting your application on top of virtual thread, this gain of performance comes from the fact that your reactive framework may be not that good, and you should not make this assumption, because reactive framework have been optimized for 10 years now. They are very good at doing that. Okay? But there is a big difference here, is that on the reactive model, all these little squares are lambdas, whereas on the virtual thread model, all these little squares are virtual thread wrapping your lambdas. And these lambdas may be blocking. So you move the responsibility of writing non-blocking code from the shoulders of you as a developer to the shoulders of the people who wrote the API, which is much more comfortable. No? Well, I think so. So now writing blocking code is okay. Okay? If you have a bug in a virtual thread, that's a bug in the API, and the API guys are going to fix it for you, which is great. So the code you write is the most basic code you can write. Okay? Virtual thread manage the blocking for you. Writing blocking code is what you should be doing. So writing this kind of code, which is the first code I showed you at the beginning, is actually the code you should be writing. Running reactive code on top of virtual threads is totally useless. Don't do it. Just write simple for loops, try catch, etc., while loops, if statements, instead of writing this complex virtual thread code. Okay, what is happening if you remember that we have this sneaky bug in read images? Throw illegal state exception. I don't know who wrote that. It's stupid, but it's good for demonstration. So what about the stack traces you get? Okay, if something goes wrong in read image, and you execute this in an executor service, that is this executor service that actually creates virtual thread on demand. It's useless to pull virtual thread. Don't do that. They are lightweight objects. You don't pull strings of characters or records, do you? So just don't pull virtual thread. So this executor service creates a virtual thread on demand and let it die when you're done with it. Well, here is the stack trace that you get. So you see that you have the main exception with the same stack trace. The first part of the stack trace is actually the same as previously, because it takes you to where you call the get. That's the stack trace in your main thread. Okay? But the root cause actually takes you to where you created your lambda and where this lambda was submitted to your executor service. So now you know actually what went wrong in your application and where it went wrong. Okay? There is this other stuff called structured concurrency. You can see structured concurrency as some kind of executor service. But because platform threads are so expensive, you need to create your executor service when your application is launched so that you have threads that are ready to be used and that you can reuse. Structured concurrency is built on top of virtual threads. you do not need to create them in advance. You can just create them on demand and let them die when you're done with them. So now you can deal with the loose thread problem with that. A structured concurrency, you can see that as an executor service, and it's auto-closable. So you use it in a try with resources statement. All right? You write your concurrent code, you launch your tasks, your requests, database, REST requests, whatever, in parallel within that. And once you're done with it, you close your structured task scope object. And once it's closed, it will take care of all the threads that are still running for you. And it will kill them. So no more loose threads. You remember the first bug I showed you? This code is actually fixing that bug. And what can you do with it? The pattern is super simple. You just fork your tasks, callable, runnables. You get a future-like object. It's not a future anymore. It's a little richer than that, but never mind. You can see that as a future object. You call join. Join is blocking, but you're in a virtual thread, so that's OK to block. OK, and once you call join and join returns, then you know that your data is there and you can do something with it. And that's it. And this is old, boring J2EE architect level code from 20 years ago. That is actually working. Why is it working? Because it's running on virtual threads. Without virtual threads, it wouldn't be working. Okay? What if something goes wrong in read images? Well, you get a stack trace. And this stack trace, you don't have any cause. You directly have the right stack trace. This stack trace actually takes you where your lambda was created and submitted to your structured task scope. And why is it working? Let me go back one slide. It's working because your structured task scope object was created where you need it and not in advance. So now you have something that you can debug easily. And if you put a breakpoint in it, the stack trace will take you exactly where you are in your application and not in your completable future or reactive framework. So if you take a look back, blocking a platform thread is wrong, where blocking a virtual thread is actually what you should do. If you don't plan to block your virtual thread, don't use them, because this is where you can actually gain something. Second, having a non-relevant stack trace is annoying. This is also fixed in virtual thread. Now your stack trace takes you where you are in your application and where you submitted your asynchronous task. Having loose threads is annoying, and when I say annoying, it's really annoying, because you need to reboot your application to fix that, or to spend hours reading your code. Now, no more loose threads, thanks to the fact that you can close your structured task scope, because letting virtual thread die is actually not a problem. So it means that using that is as efficient as your reactive framework. And don't get me wrong, you cannot be more efficient than that, despite what you read somewhere on the internet. It gives you a simple programming model, which is the good old imperative programming model. You have for loops, if statement, try catch, everything. No problem with that. It makes debugging and profiling just easy. So it fixes actually all the problems you had with the classical thread model and reactive programming. I don't have much time to talk to you about scope values. Scope values are meant to replace, well, not to replace, but to provide another programming model that is simpler than thread local variables. Thread local variables are all over the place. If you're using Spring Boot, you're actually using thread local variables very heavily. There are many flaws in their design. When I say flaw, it's a flaw in 2025, right? But the thread local class actually is from Java 2. That was more than 25 years ago. They are mutable. The VM can optimize them because they are attached to a thread that lives forever. Actually, thread local variables were made before the executor service pattern, at a time where people were creating platform threads on demand and would let them die after that. So they didn't bother removing them because the thread was to die anyway. But in 2004, when the executor service pattern arrived, then putting thread local variables on threads would actually give the possibility to keep them forever. So if you're using thread local variables, remember that you have a remove method on them, right? And if you don't know that, that's probably the source of many bugs, including security bugs in your application. So the first thing to say is that virtual thread support thread local variables. So if you want to move your application to virtual thread, you can do that, and your thread local variable will still be working. But you can do much better than that. You can use scope value, and the programming model is super simple. You just create a scope value like that. You bind it to a value. You bind a value to this scope value variable, okay? And then when you run a runnable within this context, you can read the value of this scope value. You can check if it's bound, and if it's bound, you can call get. And if it's not bound, then you cannot read it, obviously. Scope values are not transmitted from a thread to another thread because you want to get rid of loose scope values. And the virtual thread can live forever, as well as a platform thread. So if your callable is actually creating a thread, whether it's virtual or platform, the scope values will not be transmitted to that thread. But structured task scope, on the other hand, are bound. Create threads that are bound because they are auto-closable. So you know that when you leave your method, your callable, the structured task scope will be closed automatically. So if your runnable is creating structured task scope objects, the scope value will be transmitted to all the virtual threads created by this structured task scope object. And the key to understand that is that you don't want to have loose scope values in your application. So all this is fixed with thread local variables. Scope values fixes the problem of thread local variable. There are also implementation details which make them immutable and much more efficient to access than thread local variables. So structured concurrency and scope values are still preview feature in 24 and should also be preview features in 25. So if you want to check that, you need to follow what's happening on the Loom project for that. What's the plan for the JDK 23 and 24, by the way? Virtual threads are final, so they will remain final. This is not going to change, right? Structured concurrency is still in preview in 23 and in 24. If you want to check structured concurrency, I encourage you to download actually the early access version of Loom that you can find on the Loom webpage, because you have the new version of the structured concurrency API, which differs from the version you have in 23 and 24, and the same for scope values. That being said, Loom is great. Don't forget to put 5 stars on this presentation. Thank you.